Hi guys, so this video will be a continuation of the previous part 1 video on chapter 16 or unit 16, system software and virtual machines. So let's start looking at the next section, which is on multitasking. Right. Now, if you remember, we already looked at something similar to multitasking before. So we looked at pipelining initially, then we looked at something called parallel processing, and then today we are going to look at multitasking. So remember that although they might look and feel like the same thing, there are three different processors done in three different ways by the CPU. So in multitasking, it's defined as a function that allows a computer to execute more than one task or process at a time. So that's not too difficult to understand, right? Now, you might be wondering, isn't this the same as parallel processing? Not exactly, guys. Let me help you understand the difference between these things. So, in parallel processing, what you have is instructions being sent into separate cores of a CPU. So let's imagine that these three boxes denote three cores. I'll label them as core 1, core 2 and core 3. The separate processors, which are labeled as P1, P2 and P3 for example, would go into these separate cores given that the processors execute independently of each other. That's parallel processing. So you have processors or instructions that are being executed simultaneously by multiple cores of a processor. But in multitasking, it's again where you're executing more than one task at a time. If you look at the definition of multitasking again, it's the process of executing more than one task or process at a time. So again, in other words, more than one task simultaneously. But remember, in the definition, there is nothing about cores or using multiple processors mentioned, right? What that means is, in multitasking, you use a single core, which are labeled C, or a single processor, if you may. But what happens is, the processor is sent the incoming processors in some inherent order, right? So the idea is P1 goes in, and then P2 might go in next, and then P3 might go in next. Now you might be wondering, isn't this just normal processing? There's a slight difference, guys. Here you are sending the processors into the processor via a scheduling algorithm. And here, although it looks like process 1 is going in and then process 2 is going in, what might happen is, just because process 1 goes into the CPU core, process 1 might not finish running. So what will happen is, there might be a remaining task that needs to be continued to do in process 1, but the process 1 runs out of its allocated time in the processor and therefore goes back into this so-called queue until it gets more time. And I think we discussed this when we discussed the round robin process in the last video. So you might understand, you are not executing a single process until it's finishing. You are sending a process in, and then you're basically going to give that process a certain time to finish executing. But if it doesn't finish executing in that time, it will be sent back into this queue for it to wait until it's given more time, right? So that's what multitasking means here. So even though this might not look like multitasking to us, guys, it's actually literally going into the processor linearly. The difference is that since a process might not execute in one go and it will end back on the ready queue for further execution, this is effectively where you're doing one task a little bit and then doing the other task and hopefully coming back to the previous task again at a later time. That's what multitasking means. So you're not going to do two things at the same time, rather at a lower level you're doing one thing at a time. But if there is one process, you will do a bit of it, do a bit of the second task, do a bit of the third task, and then come back to the first task if it needs to do a bit more if the task wasn't finished the first time around. So multitasking is actually sort of linear, but since you're not finishing the entire task in one go, finishing a portion of it and leaving the rest for later, you can call it multitasking because you will effectively do a bit of some processes and repeat those processes again and again and again until you finish executing the entire set of processes. Now again, this is not the same as pipelining, where in pipelining it's a little different, right? In pipelining, what you do is you look internal to a process itself, where you break a process down into the 5 pipeline stages: instruction fetch, instruction decode, operand fetch, instruction execute, and write back. And you're going to execute processes stage by stage, such that when one processor stage is taking place, you can do another processor's different stage at the same time. So pipelining is internal to stages, where you're still using one core but you're sending processors in based on its stages of pipelining. In multitasking also you'll be using one core, but you'll be sending the processors in based on a scheduling algorithm. And in parallel processing, it's sort of like the highest level, where you are sending processors independently of one another to separate cores of a computer's processor. Right, so let's move on. Multitasking is carried out by the operating system kernel via scheduling algorithms, right? That's basically what I said. The scheduling algorithm is basically like an assistant that's sending people to meet the boss on an appointment basis. So if this is the boss and this is the assistant, if there are people lined up to meet the boss, the assistant's job is to sort of pick one guy and send him to the boss, pick another guy and send him to the boss, right? He or she is going to be the one that's going to allocate a so-called schedule to the incoming people to meet the boss. So this is our scheduling algorithm from a computer point of view. We also call it the scheduler. This is our CPU, and these little men or women waiting in the line are our processors. So basically multitasking, basically sending multiple people to the CPU based on scheduling algorithm, is called multitasking. And there are two types of multitasking operating systems. There's something called preemptive multitasking and non-preemptive multitasking, or preemptive scheduling and non-preemptive scheduling. Preemptive scheduling is like the true multitasking, where a process that wants to go to the CPU is allocated the CPU for a fixed time interval. So it's sort of like taking an appointment to meet the doctor. You go to the doctor, get the appointment, but then you won't finish off that consultation in one go. You might get another appointment at a later time. So either you finish the consultation in one go, or if you can't finish it in that time, you'll be asked to come back again. So you're given a fixed time interval, just like how patients are given a fixed time interval when they're trying to visit the doctor, after which they are preempted. Preempted means to sort of exit the CPU, sort of like go from running state to exit state. And then in this type of scheduling, a process can switch between the following states. A process can go from running to ready, where a process will execute in its time quantum, then go back to the ready queue to await more time. Or a process that is already blocked due to some interrupt, or since it is waiting for some input, might go back to the ready queue as well. So these two process stages, specifically running to ready and block 2 ready takes place in preemptive scheduling. Non-preemptive scheduling is not like a doctor, but rather like a supermarket counter, where in a supermarket they don't just like bill half the items and ask you to come tomorrow to bill the rest of the items, right? In a supermarket, you go to the counter, you bill everything. Even if you have one item or 100 items, they'll have to bill everything and then send you out. So it's not like giving you a fixed time slice. In non-preemptive scheduling, a process is allocated to the CPU until it terminates or switches to a waiting or block state. What it means of waiting or block state is basically, think about something like this, where you come into the CPU, or actually not, you can't come into the CPU literally, but you come into the supermarket counter and you tell the counter person, wait, hold on, I want to get one more item and come, right? So therefore, when something like that happens, when the counter or the cashier's process is interrupted, the entire cache is sort of blocked, right? That's what it means to switch to a waiting or block state. So a process is allocated to the CPU until it finishes, like until you finish billing all your items in the cart, or until you switch to a waiting or block state, which is like you telling the cashier, please wait, let me get one more item and come back. So in this scheduling system, what can happen? A process that is in a running state can go to the block state, and a process that is in the block state can come back to the running state. So just a quick comparison between preemptive and non-preemptive scheduling. In preemptive scheduling, resources are allocated to the process for a limited time, just like a doctor's appointment, right? But in non-preemptive, resources allocated to the process throughout burst time or until waiting state is reached. Burst time, again, if you remember from the last video, is the total time a process takes control of the CPU, right? So this is sort of like supermarket counter. So you can always think about preemptive scheduling like a doctor's appointment, whereas non-preemptive scheduling is like the supermarket counter. In preemptive scheduling, a process can be interrupted, whereas in non-preemptive scheduling, a process cannot be interrupted. What I mean by that is that in non-preemptive scheduling, since you have to finish the entire process, a process cannot be interrupted midway, right? So like the cashier has to bill all your items. They can't take another person while you are being billed your items. But in preemptive, the idea is, since a doctor's appointment is allocated for a fixed time, even though you get that fixed time, you might not finish the doctor's appointment in that fixed time. You will come back later. So since your sort of since your consultation with him is broken down into parts, after the first part is over, another process can come along, another patient can come along. So just like that, a process can be interrupted in preemptive scheduling. Furthermore, the problem with preemptive scheduling is that low priority processes may be starved. What that means is, basically, in preemptive scheduling, the processors go into the processor on a priority basis. Because of that, low priority processors might sort of have to wait for a long time until they finally get the time or get the opportunity to go into the CPU. So low priority processors may be starved in preemptive scheduling, whereas in non-preemptive scheduling, what happens is you need to finish an entire process before you can go to the next. So think about a supermarket counter. If there's people with 100 items in their cart, and if there's like one person behind that dude that has just one item, that dude has to wait until all those 100 items in front of him are billed, right? So processors that have a short time, that take a short time, are starved. They have to wait until the longer ones finish. So therefore, all in all, preemptive is considered a flexible form of scheduling, whereas non-preemptive is considered a rigid form of scheduling. That's all. Preemptive and non-preemptive are very important. Next up, we learned about two schedulers last video, right? We'll look at them in detail. First up comes the high-level scheduler. The high-level scheduler is where it's a program that admits new processors into the ready queue. High-level scheduler brings in new processors to the ready queue. Basically, this scheduler is also referred to as the job scheduler, right? And then a low-level scheduler picks processors from the ready queue to the CPU. This is sort of like the boss's assistant. Boss's assistant, where the boss is the CPU. The low-level scheduler is like the boss's assistant who is picking people from the queue and sending him to the boss. A low-level scheduler decides which process should be executed next and allocates the CPU to it. So high-level scheduler brings new processors to the ready queue. Low-level scheduler brings processors from the ready queue to the CPU. Basically changes process state from ready to running. And this is done based on process priority. So just because a process is ordered like this, A, B, C, D, let's say there are 4 processors in the ready queue, A might not go to the CPUs next if it has a low priority. If B has a higher priority, it might go into the CPU and A might have to wait, right? So low-level scheduler picks people from the ready queue to the CPU based on process priority and not the position of the queue. Keep that in mind, very important. It depends on process priority. And basically, the low-level scheduler has 3 main objectives. Its objectives are to maximize system throughput, basically make the system operate in the most efficient and fastest manner, ensure acceptable response time, which means that the scheduler's job is, if you let's say you press the mouse button, the left mouse button on your mouse, it shouldn't take 2 seconds or 3 seconds for the mouse button's response to be received. Like if you press a button on the computer, you should hopefully get back the response to that button press immediately, right? So that means that process should be sent into the CPU and the process must be executed almost immediately. So therefore, it's a low-level scheduler's job to make sure processors like that are executed immediately and therefore ensure acceptable response time. And all in all, it helps ensure that system stability is consistent. That's all. Now, the next thing we'll look at is process priority. Basically, we know that the low-level scheduler picks processors from the ready queue into the CPU based on priority. But what are the factors that affect priority? There are multiple factors, and I'll mark sort of the important ones here. Process category, CPU bound or IO bound, turnaround time, waiting time and response time, deadline and total burst time. So I've just marked stars for the most important ones, but I'll discuss everything, right? It's just that you can just remember these rather than remembering everything, because we have a total of around 8 different process priority guidelines here. So first of all, process priority depends on several different factors. The first being process category. Batch processors, online processors and real-time processors might have different priorities. What does that mean? A batch process is a process that's taking place over a prolonged period of time. So therefore, a batch process might have low priority because it's taking place sort of in the background. Sort of like, maybe copying files from a hard disk drive to your USB. Those are sort of batch processors. They do not require immediate execution, but they should take place in the background. Online processors are processors that take place online. And what does it mean to be an online process? It means that the process is waiting and executing with the user, sort of. So a batch process might be like copying files, whereas an online process is one that's taking place now, but sort of with the user, not automatically. So maybe a process, something that takes place at an ATM, for example. The ATM's processors wait for the user to input, then do a small task. Wait for the user input again and then do a small task. So it's constantly online awaiting user input. Real-time processors are processors that take place sort of independently of the user, rather automatically. So stuff like calculations that take place under the hood, maybe maybe something like a video that is downloading, right? Or maybe you're training some machine learning algorithm in the background. They are being taken place right now, then and there. So that's real time. So process category will also affect priority. Then whether processors are CPU bound or IO bound also influences this priority. CPU bound processors are processors that take place in the CPU, usually associated only with the CPU. So stuff like mathematical calculations, calculating factorials, training neural networks, all of that stuff takes place inside the CPU with very little use of external devices. But IO bound processors also depend on other devices such as the printer or the mouse. Maybe playing games and waiting for the character to move might be an example of an IO bound process. Now after that, another process priority influencing factor is resource requirements. Whether that process requires a lot of resources like a lot of RAM, a lot of IO devices, or is it something that's requiring very little processors. And then turnaround time, waiting time, and response time. Now I'll leave this for later because we'll discuss what turnaround time, waiting time, and response time is. For the moment, we'll keep that out the door. 5. Whether the process will be interrupted. Basically, if it's a process that the CPU knows that will be interrupted, those processors might have less priority, because processes that are bound to be interrupted might not need to be executed right now, whereas there might be other processes in the CPU ready queue that need to be executed immediately and will not be interrupted. So what does it mean for a process to be interrupted? That means the process, while it's going on, another interrupt will come along, another process will come along that demands the processor's attention. So if a process itself would create an interrupt, then that process would have a different priority to normal processors that don't require interrupts. Next up, other factors that influence process priority is the deadline for completion of the process. There might be some processes that need to be completed before another process takes place. So such processes that are time bound would have higher priority. Next up, the total burst time. The total time it takes for a process to run will also influence its priority. And finally, last but not least, the memory requirements of a process. This is a process. Is this process going to take 1 GB of the RAM, or is this process going to take like just 1 MB of RAM? Processors that take a lot of RAM might have higher priority. Right, so that's process priority. And what we'll look at next is sort of what exactly happens to the CPU when a process actually comes into it. So when we look at a CPU, guys, I want to sort of dive into this conversation of CPU IO burst cycle. When a process comes into the CPU, its frequency increases exponentially, forming a peak as shown below. So basically, guys, what you can do is you can look at this graph. This graph has two axes. This y-axis shows the CPU's current frequency. Basically, at what frequency is the CPU running at. Now let's say that your CPU is rated at 3.5 gigahertz. Does it always run at 3.5 gigahertz? No. What CPU processor manufacturers usually quote as the speed is the base speed or the base frequency of your processor. But that means that the processor can run at higher speeds and will most often run at lower speeds as well. Right? So this frequency can change depending on how busy the CPU is at a given time. So it's sort of like our heart rate. When we are doing a lot of exercise, our heart rate increases, and when we are not doing a lot of exercise, our heart rate might reduce. The same thing applies to a CPU. So as soon as a process goes into the CPU, the CPU sort of gets excited and its heart rate or frequency increases. So as soon as the process is taken in by the CPU, you'll see that the frequency jumps up. But then soon after that, it gets sort of back on track. But what you need to understand is that as soon as the process comes in, the CPU's frequency increases exponentially. So you can think about it like our heart rate increasing, or for those that do biology, sort of like the neuron activation curve, right? That's the idea. Now, after this point, the graph can change, right? Depending on the processor's type. A process can either be CPU bound or IO bound. You might remember the conversation we had earlier. A CPU bound process is a process that requires the CPU for most of its work. An IO bound process is a process that requires the CPU but also might be frequently sent into the blocked queue since it's waiting for some IO operation. So CPU bound operations are mainly mathematical and scientific operations. Basically operations that heavily rely on registers and the arithmetic logic unit. IO bound operations might be basically any operations associated with input output devices. So stuff like a word processor. Any process associated with a word processor might constantly wait for this user to type something into the keyboard. A game might be an IO bound process. So depending on which type of process it falls into, this curve shape from this point on might change. Now if it's a IO bound process, what does it mean? What it means is that this process spends more time doing input output operations than actual computation. So therefore it will have short CPU bursts. The idea is, if you plot the curve for an IO bound operation, guys, in an IO bound operation, you will see that the CPU will have sudden increases and decreases of CPU frequency. But at no given time would the CPU frequency be sort of high for a long time. It will quickly increase and suddenly drop. Why do you think is the reason for this? Because as soon as a process comes into the CPU, it can only do little computation before it has to be sent to the blocked queue waiting for some input output. So it cannot therefore finish doing its work. It needs to sort of be blocked. So it's doing some processing, then it's blocked. It's doing some processing, then it's blocked. So you see short CPU bursts in an IO bound operation. In a CPU bound operation, guys, since the process comes in and maximizes the CPU's throughput for its entire process, you'll see that you'll have very long CPU bursts, right? Like that. Because it will spend more time actually maximizing the CPU's infrastructure. You'll be using the ALU, you'll be using the registers, you'll be using the accumulator. So the CPU has to do a lot of work, and therefore, since it's CPU bound processors, it will do more work over a longer time pertaining to the CPU and the CPU only. It doesn't work with any other IO for the most part, and therefore it might not get blocked. So therefore, CPU cycle shapes for CPU bound operations will have very long CPU bursts. Right. Now, soon after this, what we'll look at is how we measure times in the CPU. We'll quickly go through this because this stuff is not very important, but let's go through this really quickly. CPU processors have several time measurements. The first time measurement being arrival time. Arrival time for a CPU process is the time at which a process arrives in the ready queue. Remember, the high-level scheduler always has to take a new process and put it to the ready queue, right? The time it arrives at the ready queue is called the arrival time. Then completion time is therefore pretty self-explanatory. If arrival time is the time that a process arrives in the ready queue, the completion time is the time that a process completes its execution, right? So arrival time is not the time that a process is taken into the CPU. Arrival time is the time that the process arrives at the ready queue. But completion time is the time at which the process completes its execution. Keep that in mind, don't confuse Don't confuse yourself that arrival time is when the CPU takes in a process. It's when the ready queue takes in a process. Burst time, you guys already remember, time required by a process for CPU execution. Next up, we have something called turnaround time, a word that I left behind from the previous discussion. In turnaround time, guys, turnaround time is the time difference between completion time and arrival time. So if you want to calculate turnaround time, it's basically the completion time minus the arrival time of a given process. So if you can think about what this turnaround time means, it's basically the time it takes for a process to end up on the ready queue, be executed by the processor, and then finish executing. So the time it arrives at the queue to the time it finishes executing, from the time it arrives at the queue to the time it finishes executing, is the turnaround time. It's usually a good idea for any low-level scheduler to minimize turnaround time for any given process. Minimizing turnaround time is another important task that all processors, low-level schedulers must adhere to. Waiting time is the time difference between turnaround time and waiting time. Turnaround time and burst time. So what does that mean? Turnaround time is the time it takes for a process to arrive at the ready queue until it finishes executing. What if you minus the burst time from that? The burst time is the time it is inside the CPU. So what remains? What remains is the time it has been waiting, right? If the burst time is the time it was executing, everything else from the start of the processor's arrival in the ready queue is time it was waiting. It wasn't doing anything. So waiting time is calculated by doing turnaround time minus burst time. So keep that in mind, very important, turnaround time and waiting time. So now we know turnaround time and waiting time are also things that affect a processor's priority. And that's all we'll be looking at in this video. In the next video, we'll actually dive deep into non-preemptive and preemptive scheduling routine algorithms. Remember at the beginning of the lesson we discussed multitasking means that you send processors into the processor based on some scheduling algorithm. The low-level scheduler picks the job from the ready queue to the CPU, but it's actually controlled by a scheduling algorithm. So in the next video, we'll actually look at what these scheduling algorithms are. See you then. Bye-bye.